Welcome to Tech Girl Kannada YouTube channel. Applied Chemistry for CSE stream. Syllabus, Sensors and Analytical Techniques. Syllabus, Sensors, Introduction, Types of Sensor, Working Principle of Electrochemical Sensor, Electrochemical Sensors for the detection of pharmaceuticals, diclofenac and hydrocarbons, 1-hydroxypyrene. Electrochemical gas sensors for the dissolved oxygen, electrochemical gas sensors for detection of toxic gases, NO2, SO2, disposable sensors in the detection of biomolecules, ascorbic acid and pesticides, glyphosate. Sensors in analytical techniques, working principle, instrumentation of optical sensors, calorimetric sensor and its application in the estimation of copper, working principle and instrumentation of potentiometric sensors and its application in the estimation of iron, principle and instrumentation of conductometric sensors and its application in the estimation of weak acid sensors. Sensors are devices used to detect the presence of chemical species and monitor physical parameters like temperature, humidity, etc. There are different types of sensors like gas sensors, chemical sensors, and biological sensors, developed for various purposes and applications. Electrochemical sensor. Electrochemical sensor is a device which converts the information associated with electrochemical reactions, the reaction between an electrode and analyte, into an applicable qualitative or quantitative signal. They are mainly divided into three types: potentiometric, conductometric, and amperometric or voltammetric. Working of a sensor. The basic components of sensor are receptor, analyte, product, transducer, processor, detector, display. Receptor. It is a sensing element made of chemical or biological molecule capable of interacting with analyte and producing analytical signal proportional to the concentration of analyte. Transducer. It is an electronic device capable of converting analytical signal into electrical signal. Processor. It is the process the electrical signal and transmits into a readable or measurable form. Detector. It detects the reading in various forms as digits, graph, time, etc. to display on screen. Properties. Sensors are selectively sensitive to particular type of chemical species. Analyte have ability to interact with the exceptionally small concentrations of analyte and send signal. Increased sensitivity and fast response. Available in compact instrumentation size. Have ability to expand previous and existing analytical detection range. Cost effective and eco-friendly. Applications. Electrochemical sensors have been used in military and defense applications for the detection of explosive or toxic gases, to detect various polluting chemicals in the atmosphere, in biomedical applications for early detection of disease, toxins, to monitor physical parameters such as temperature, humidity, etc., to monitor glucose in blood, to study neurotransmitters in brain for understanding neurophysiology, in food industry, to determine the quality and freshness of food samples, in agriculture to detect the soil humidity, pesticide, insecticide residues, and nutrient requirements. Electrochemical sensor for the measurement of dissolved oxygen DO. Dissolved oxygen is a key measure of water quality relied upon in various applications. In industrial water treatment, dissolved oxygen levels can be an indicator of waste quality issues that lead to corrosion of equipment. In aquaculture, fish transport and aquarium applications, dissolved oxygen is monitored to ensure that aquatic species have enough oxygen in their habitat to survive, grow, and reproduce. The concentration of dissolved oxygen in water can be monitored continuously using a dissolved oxygen sensor. The working of dissolved oxygen sensor depends on the type of sensor used. Commercially available dissolved oxygen sensors are of two types, that is, electrochemical dissolved oxygen sensors. Electrochemical dissolved oxygen sensors. They measure dissolved oxygen concentration in water based on the electrical current produced. There are two types of electrochemical DO, that is dissolved oxygen sensors. Galvanic dissolved oxygen sensors. They consist of two polarized electrodes, zinc as an anode and silver as cathode, and an electrolyte solution such as sodium hydroxide. The electrodes and electrolyte solution are isolated from the sample by a thin semi-permeable membrane. Polarographic dissolved oxygen sensors. They consist of a silver anode and a gold cathode and an electrolyte solution such as KCl. The electrodes and electrolyte solution are isolated from the sample by a thin semi-permeable membrane. Optical dissolved oxygen sensor. They measure dissolved oxygen concentration in water based on quenching or luminescence in the presence of oxygen. They can measure either the intensity of the lifetime of the luminescence, as oxygen affects both. Measurement of dissolved oxygen by DO sensor. Working principle in an electrochemical dissolved oxygen sensor. The dissolved oxygen diffuses from the water sample across an oxygen permeable membrane into the sensor, wherein the oxygen undergoes a chemical reduction reaction producing an electrical signal. This signal can be read by a dissolved oxygen instrument. Procedure: anode, that's silver, electrolyte, KCl and H2O, cathode, AU, that is gold or platinum. Inert electrode does not participate. Inert electrode here in this thing is platinum. Here is the figure of DO sensor. Cathode, that is gold. Anode, it's silver. Electrolyte, KCl and H2O, gas, permeable membrane. Electrochemical dissolved oxygen sensors consist of two polarized electrodes, an anode and a cathode, in an electrolyte solution. The electrodes and electrolyte solution are isolated from the sample by a thin semi-permeable membrane. Dissolved oxygen diffuses across the membrane at a rate proportional to the partial pressure of oxygen in the water. The dissolved oxygen is then reduced to the consumed at the cathode, resulting in the production of an electrical current that is directly related to the oxygen concentration. This current is carried by ions in the electrolyte and runs from cathode to anode. As this current is proportional to the partial pressure of oxygen in the sample, it can be calculated by the following equation. ID, current produced, is equal to 4F, Faraday's constant, 96500 coulomb per mole, POML. What does that mean? Permeability of the membrane as a function of temperature. Here, permeability of the membrane, that is PM. It is also a function of temperature. A, surface area of cathode. PO2, partial pressure of oxygen, divided by D, membrane thickness. Now, electrode reactions can be written as anode reaction. 4Ag gives 4Ag plus 4 electrons. 4Ag plus 4KCl gives 4AgCl plus 4K plus. Now at cathode, O2 plus 4E minus plus 2H2O gives 4OH minus. 4OH minus plus 4K plus gives 4KOH, which is an alcohol. Overall reaction can be written as O2 plus H2O plus 4KCl plus 4Ag gives 4AgCl plus 4KOH. Electrochemical sensor for pharmaceuticals. Pharmaceuticals are simple, complex, organic molecules essential to combat ill health. After usage, they enter into the ecosystem through waste and cause adverse effects on living organisms, even if they're present at low concentration. Therefore, to monitor the presence of these pharmaceuticals in the ecosystem, development of reliable, stable, low cost, rapid analytical tool is required. So there are several methods for the purpose, but electrochemical sensors are the best option for the detection of pharmaceuticals. Determination of diclofenac. Determination of diclofenac. DF is a non-steroidal anti-inflammatory drug. Diclofenac is a non-steroidal anti-inflammatory drug used for the treatment of headache, mild migraine, muscle pain, dental pain, rheumatoid arthritis, and osteoarthritis. DF. Diclofenac has no side effects when taken in the proper doses, but an overdose can cause adverse effect on human body. Moreover, the presence of diclofenac in ecosystems directly affects the health of living organisms. Even if it is present at trace, electrochemical sensing methods have been commonly used to detect DF. Diclofenac sensor consists of working or sensing electrodes such as nanostructured carbon coated with gold nanoparticles and a counter electrode which are separated and immersed in an aqueous solution of acids or neutral solution. When the diclofenac molecule comes in contact with a sensing electrode, diclofenac is oxidized to 2,6-dichloroaniline and 2,2-hydroxyphenyl acetate by the loss of an electron and H+. Proton and electron react with 2,2-hydroxyphenyl acetate on the counter electrode, producing 1-hydroxy 2,2-hydroxyphenyl ethanolate. The current thus produced from the reaction is monitored and used to calculate the concentration of DF, that is diclofenac, present in that. That is electrode reactions, anode reaction. Here the names are not given. When this DF molecules is get in contact with the water, that is H2O, which in turn gives the thing as electron and one H plus ion along with the 2,6-dichloroaniline and 2,2-hydroxyphenyl. You can see with the loss of an electron H plus. Then the cathode reaction, this 2,6-dichloro, then what is that? Yeah, 2,2-hydroxyphenyl will be become by the action of the proton, that is H plus, it will become a counter electrode producing 1-hydroxy 2,2-hydroxyphenyl. Electrochemical sensor for hydrocarbons. How to sense these hydrocarbons? Like oxides of nitrogen, carbon, and sulfur, the presence of hydrocarbons in the atmosphere is also dangerous. Among hydrocarbons, polycyclic aromatic hydrocarbons PAH are persistent organic pollutants widely found in the atmosphere, soil, water, and food. The incomplete combustion of coal, gas, wood, garbage, and tobacco results in the formation of PAH. PAHs can enter the human body through respiration, diet, and contact. They are known to be carcinogenic. After entering the body, some PAHs are metabolized into hydroxyl PAH or OHPAHs. Hence, human exposure to PAHs is an important factor to reveal their toxicity and carcinogenic risk. Therefore, it is essential to develop an Analytical technique to monitor the presence of hydrocarbons in the ecosystem. Electrochemical sensor is one of the best techniques. Determination of 1-hydroxypyrene, OHP. 1-hydroxypyrene. 1-hydroxypyrene belongs to the class of polycyclic aromatic hydrocarbons. If its concentration is beyond the limit, it will affect the life of both plant and animal, thus causing asthma, cancer, bronchitis, etc. Electrochemical sensing methods have been widely used to detect OHP. Working principle. The 1-hydroxypyrene sensor consists of a glassy carbon electrode coated with chromium containing metal organic framework as the working electrode, Ag silver or AgCl, silver chloride as the reference electrode, and a platinum wires as a counter electrode, which are separated and immersed in 0.05 m phosphate buffer pH 2.0 containing 0.2 m NaCl solution. 1-hydroxypyrene is electro-oxidized to several hydroxylated species and then hydroquinone by losing 2 electrons and 2H plus when a constant potential of 0.7 volt is applied. The current produced from these reactions is directly proportional to the concentration of analyte, is monitored and used to calculate the concentration of 1-hydroxypyrene electrode reactions. Here, anode reaction have been given as 1-hydroxypyrene plus water, 2 electrons plus 2 protons, that is 2H plus ion, 1,2-pyrineediol, where another OH attached to this 1-hydroxypyrene is called 1,2-pyrineediol. 1,2-pyrineediol then becomes, its intermission stage. This further becomes 1,2-pyrineedione. It was diol at first and then became dione by oxidizing itself, which is giving further 2 electrons plus 2H plus ions. Cathode reactions. This 1,2-pyrineedione plus 2 electrons plus 2H plus ions again becomes 1,2-pyridiol. Electrochemical sensor for gaseous analytes. Electrochemical gas sensor is an amperometric type sensor used to determine the concentration of gaseous analyte like air pollutants such as COX, NOx, SOx, leakage of chemicals in industry such as cyanides, etc. It consists of a membrane, reference electrode, working electrode, and counter electrode dipped in an electrolytic solution. The designing of gas sensor depends on the type of gaseous analyte to be detected. Capillary gas diffusion SOx, hydrophobic membrane sensing electrode, reference electrode, counter electrode, electrolyte, along with connected to the voltmeter and the amperemeter. The main components of the gas sensors are filter. It allows only the analyte of interest to enter inside the sensor membrane. It is hydrophobic semi-permeable membrane which regulates the inflow of gaseous analyte. Its pore structures will not wet by water molecules of electrolyte, helps the easy diffusion of gas onto the working electrode surface. Electrodes. Reference, working and counter electrode. The selection of receptor on working electrode depends on the type of gaseous analyte to be detected. Electrolyte, acidic, basic or neutral solution having good ionic conductivity is used as an electrolyte for better transport of ionic species. It must be physically and chemically more stable. Working principle. Diffusion. Gas diffused through the filter and then through the membrane onto the working electrode surface. Adsorption. Gas adsorbed on the working electrode surface. Reaction. Oxidation or reduction reaction takes place on working electrode surface by losing or gaining electrons. Flow of electrons will flow through the external circuit. Electrical signal. Electrical signal is generated depending on the concentration of analyte. Processing of electrical signal and its transmission into readable form. Desorption and removal of products from the electrolyte. Electrochemical gas sensors to determine NOx. Nitrogen oxide is the general term for a gas mixture composed of different oxides of nitrogen, often expressed as NOx. Monitoring NO levels becomes essential in the diagnosis of cardiovascular problems, since nitrogen oxide is a key vasodilator. Okay, working principle. The working principle of all electrochemical gas sensors is same, but the selection of receptor to be coated on working electrode and the use of electrolyte are different. They depend on the type of gas to be detected. Capillary gas diffusion. Nitrogen oxide, a hydrophobic membrane. Capillary gas diffusion. Sensing electrode, reference electrode, counter electrode, electrolyte. Sensing electrode, reference electrode, counter electrode, electrolyte. Ammeter and voltmeter. For the detection, nitrogen oxide sensor consists of a working electrode WE, such as glassy carbon surface modified with cobalt 4 oxide catalyst, and platinum counter electrode CE to make it more sensitive to NO, and AgAgCl electrode as a reference electrode, which are separated and immersed in an aqueous solution of acids or bases. When nitrogen oxide gas comes in contact with the sensing electrode, it gets oxidized and oxygen gets reduced on cathode. The current thus produced from the reaction is monitored and used to calculate the concentration of NO. Anode reactions. NO is solutions is directly electro-oxidized in 3 steps. NO gives NO plus E minus. NO plus OH gives HNO2. HNO2 plus H2O gives NO3 minus plus 2E minus plus 3H plus. 3H plus, how it gives 3H plus, HNO2, H2O, NO3, 3H plus, 2E minus. Cathode reaction, 2H plus half O2 plus 2 electron gives H2O. For the detection of NO2, sensor consists of working electrode WE, such as AU gold, platinum, naphthalene, and platinum counter electrode to make it more sensitive to NO, and AgAgCl electrode as a reference electrode, which are separated and immersed in an aqueous solution of 10 H2SO4. When NO2 gas comes in contact with the sensing electrode, it gets reduced to NO. The current thus produced from the reaction is monitored and used to calculate the concentration of NO2. Reaction NO2, 2H plus 2E minus, NO plus H2O. Electrochemical gas sensors to determine SOx, that is sulfur oxide. Sulfur oxide is a generic term for a gas mixture composed of sulfur and oxygen, of which sulfur dioxide is naturally present in the atmosphere at very low concentrations but can be harmful at higher concentrations. The major source of sulfur dioxide pollution is the combustion of coal and petrol containing sulfur. Sensors are used to monitor sulfur dioxide. Working principle. Working principle. SO2 gas sensor consists of hydrophobic membrane, AU naphthalene sensor electrode, counter electrode, and the reference electrode with 0.5 m H2SO4 as electrolyte. SO2 gas molecules diffuse through the semi-permeable membrane into the sensing electrode, undergo oxidation producing sulfur dioxide, that is SO3, as well as protons and electrons. Protons and electrons reduce oxygen on the counter electrode, producing water. The current thus produced from the reaction is monitored and used to calculate the concentration of SO2. Capillary gas diffusion, SOx. Hydrophobic membrane, sensing electrode, reference electrode, counter electrode, electrolyte. Electrode reaction. Anode reaction, SO2 plus H2O gives SO3 plus 2H plus 2 electrons. Cathode reaction, half O2 2H plus 2 electrons gives H2O. Electrochemical biosensors. Biosensors are the devices used to detect biomolecules like nucleic acid, hormones, glucose, etc. Various biosensors are used for industrial, agricultural, and clinical applications. The main component in biosensor is a bioreceptor, which is capable of interacting with the bioanalyte. The bioreceptor is an immobilized biological molecule like enzyme, hormones, nucleic acid, etc., which is selectively and sensitively interacts with the analyte and produces analytical signals. This analytical signals is detected and converted into a readable electrical signal by the transducer as shown below. Bioreceptor, transducer, sensor, and display. Analyte, physiochemical signal, electrical signal. immobilized biological molecule enzyme, optical, electrochemical, thermic, gravimetric, anything sensor. Next, disposable sensors. What is this disposable sensors? Are low cost, easy to use sensing devices designed for short term or rapid single point measurements. They are low cost, stable, reliable, smaller, lighter, easy to use, time saving, highly selective and sensitive, and highly advantageous over classical sensors. These types of disposable sensors are extensively required for the analysis of samples from industrial, agricultural, and clinical fields. Disposable biosensor consists of a reference, working, and counter electrode, which are coated on a special type of paper strip by using screen printing technology. This strip is inserted into a portable meter to monitor and measure the signal. That is analyte, reference electrode, working electrode, counter electrode, LEDs. Advantages of DS. It is disposable sensors over classical sensors. Cost effective. Disposable sensors are typically cheaper than classical sensors. Convenient. Disposable sensors do not require calibration or maintenance. Hygienic. Disposable sensors can help reduce the risk of cross contamination in medical and food safety applications. Portable. Because disposable sensors are typically smaller and lighter than classical sensors. Rapid testing. Disposable sensors can provide results quickly, allowing for faster decision making. Reduced waste, because disposable sensors are designed to be used once and then discarded. Disposable sensors of biomolecule. Monitoring of biomolecules like hormones, vitamins, nucleic acids, lipids, carbohydrates, etc. is very essential, because any imbalance in these would cause health issues like diabetic, asthma, heart attack, birth complications, etc. There are several disposable sensors developed for the analysis. The receptor and working electrode may be enzyme modified or non-enzyme modified. Considering the disadvantages of enzyme modified sensors such as fabrication and poor stability, non-enzyme biosensors have attracted increasing research interest in recent years. DS for the detection of ascorbic acid. Ascorbic acid, AA, is the key biomolecule in the physiological process of human metabolism. It is an important water-soluble vitamin C, ascorbic acid, in forming collagen, a protein that gives structure to the bones, muscles, and blood vessels. It is a potent reducing and antioxidant agent that regulates fighting against bacterial infection as well as detoxifying the reactions. Abnormal levels of AA, ascorbic acid, will lead to some disorders and diseases such as mental illness, scurvy, and anemia. Therefore, it is essential to establish a sensitive tool to detect ascorbic acid. Working principle. Ascorbic acid sensor consists of a gassy carbon working electrode, GCE, platinum counter electrode, silver chloride reference electrode, which is printed on paper strip using screen printing technology. The enzyme free active material bioreceptor like cadmium oxide, SNO2V2O5 in alkaline phase is coated on GCE, is used as sensing electrode. When ascorbic acid comes in contact with the working electrode, it gets oxidized, losing electrons, and the oxidized products of ascorbic acid gets reduced to 2,3 diketogluconic acid, which generates electric current through electron transfer with the electrode. Since the magnitude of the electric current is directly correlated with the concentration of AA, the current is produced from the reaction is monitored and used to calculate the concentration of AA. Electrode reaction at working electrode, ascorbic acid gives dehydroascorbic acid. At counter electrode, dehydroascorbic acid plus 2H plus 2,3-diketo-1-gluconic acid. Disposable sensor for pesticides. With the intention of getting good yield and to protect crop, farmers have started using varieties of pesticides. They need to be used in very low concentration, but without proper knowledge, they have been using in large amounts. This resulted in the accumulation of traces of these pesticides in soil, water, and air. The entry of these pesticides into the human blood system may cause asthma, cancer, birth problems, etc. Therefore, there is a need for developing a low-cost, reliable, sensitive enzyme modified screen-printed disposable sensors to detect pesticides. Disposable sensors for the detection of glyphosate. Glyphosate is one of the most widely used herbicides with application in agriculture, forestry, industrial, weed control, lawn, garden, and aquatic environments. Glyphosate has the capacity to bind to soil colloids and be degraded by soil microorganisms. Nowadays, glyphosate residues becoming more common in food and water as a result of extensive usage of this chemical. Glyphosate has the potential to stimulate hormone-dependent malignancies in humans and is highly carcinogenic even at a low concentration. Therefore, it is essential to design a low-cost, reliable, rapid, and sensitive tool for detection of the glyphosate. Working principle: glyphosate disposable sensor consists of a carbon paste electrode, graphite oxide paste electrode as a working electrode, platinum wire as counter electrode, e.g. TCl silver chloride as a reference electrode, which are printed on paper strip using screen printing technology. The flavoenzyme glycine oxidase is capable of selectively oxidizing glyphosate into amido-methylphosphonic acid. Glycine oxidase is immobilized on platinum decorated laser induced graphene LIG electrode and is used as working electrode. When glyphosate comes in contact with the working electrode, it gets oxidized, losing electrons and protons, leading to the formation of amido-methylphosphonic acid. The current thus produced from the reaction is monitored and used to calculate the concentration of the glyphosate. Electrode reaction: glyphosate, amido-methylphosphonic acid, then glyoxylate. Sensors and analytical techniques. Analytical techniques are the method used for the qualitative and quantitative analysis of chemical species present in sample. Volumetry and granumetry are classical methods used for the quantitative determinations. Nowadays, there are several analytical techniques like colorimetry, potentiometry, conductometry, etc. used for the analysis of chemical species. Advantages of analytical techniques: time saving. Analysis time has been reduced from several hours or days to even minutes. Accuracy. Improvement in accuracy of results by eliminating errors introduced due to personal bias. Sensitivity: highly sensitive to analyte present in the sample. Less amount of sample, micro amounts of sample is enough for analysis. Colorimetric sensors. Colorimetric sensors are electronic components designed to detect and convert incident light rays into electrical signals. Colorimetry is used for the determination of concentration of substance present in its solution. This method is used for colored solutions or solutions which produce color on treating with suitable reagent. Theory: when a monochromatic light of intensity I0 is passed through a transparent medium, a part of it is absorbed, IA, by the species, and electrons get excited. Calorimetry is used for the determination of concentration of substance present in its solution. This method is used for colored solution or solutions which produce color on treating with suitable reagent. Theory: when a monochromatic light of intensity I0 is passed through a transparent medium, a part of it is absorbed, IA, by the species, and electron get excited from lower energy level to higher energy level. Some part is reflected, IR, and remaining is transmitted, II, IT. So intensity of incident light is equal to the sum of IA, IR, and IT. I0 is equal to IA plus IR plus IT. For a glass air interface, IR is negligible and therefore I0 is equal to IA plus IR. IT by I0 is equal to T is called transmittance. Log of 1 by T is equal to log of I0 by IT is called the absorbance or optical density. The relationship between absorbance A, concentration C, expressed in mole per dm cube, and path length T, expressed in centimeters, is given by Beer-Lambert's law. Beer's law states that amount of radiation absorbed by the solution is directly proportional to the concentration C of the species in the solution. Lambert's law states that the amount of radiation absorbed by the solution is directly proportional to path length T of the solution. That is, A is equals to log I naught by IT equals to ECT, where E is molar extension coefficient and is a constant for a given substance at a given wavelength. If T, the path length, is kept constant, then A is directly proportional to C. Hence, the plot of absorbance against concentration gives a straight line. Calibration curve. Instrumentation: light source, lens, filter, sample tube, photocell, detector, recorder. Source: tungsten filament or sodium vapor lamp is used as a source of light. Filter: a device used to obtain monochromatic light of required wavelength. Sample tube: cuvette to hold the sample, usually made of glass or quartz cell. Photocell converts the emitted light into electrical signal. Detector detects the light radiation absorbed by the solution. Recorder records the numerical value. Application: for the estimation of copper. When a solution of cupric ions is treated with ammonia, deep blue colored complex is formed. The color intensity is depends on concentration of copper ion Cu2 plus for NH3 CuNH3 4 times 2 plus deep blue. Procedure: prepare a stock solution of CuSO4 by dissolving 1 gram into 50 ml of water. Transfer to 0.5, 5.0, 7.5 and 10.0 cm cube of solution into separate labeled 50 ml standard flasks. Add 5 ml of 1:1 ammonia solution to each of above solutions and also the test solution. Make up to the mark with ion exchange water and mix well. Prepare a blank solution by dissolving 5 ml ammonia in 50 ml standard flask and use the solution to set the calorimeter to 0 at a 620 nanometer. Measure absorbance to all the solutions at 620 nanometer. Draw a calibration curve by plotting absorbance versus concentration of copper, mg or ml. Using the calibration curve, determine the volume of copper sulfate in the test solution and calculate the amount of copper in the test solution. Here they have given the rough data. Volume of CuSO4 blank, volume of NH3, absorbance blank 50, 2.55, 0.06, 5.0, 5.0, 0.12 and so on. Your absorbance versus concentration of Cu graph is given, which clearly shows that absorbance is directly proportional to the concentration of Cu, volume of test solution. 249.6 gram of CuSO4 5H2 contains 63.55 gram of Cu2 plus, and we have 1 gram of CuSO4 5H2 contains 0.2545 gram of Cu2 plus. So if you calculate, you will be getting the concentration of Cu2 plus in the solution. Potentiometric sensor. Potentiometric sensor is a device used to determine the concentration of analyte by measuring the change in potential of reacting system. It is based on Nernst equation, which gives the relationship between metal ion concentration Mn plus and electrode potential E. Theory: redox titration can be carried out potentiometrically using platinum calomel electrode combination. For the reaction, reduced form, oxidized form plus electrons. The potential is given by the Nernst equation. E is equals to E naught plus 0.0591 by n log oxidation form by reduction form, where E naught is the standard potential of the system. The potential of the system is thus depends on the ratio of the concentration of the oxidized to that of the reduced species. As the reaction proceeds, the potential changes more rapidly at the vicinity of the endpoint of the titration. This may be followed potentiometrically, and a plot of change in potential against volume of titration curve is characterized by a sudden change of potential at the equivalence point, also called endpoint. Instrumentation: burette, potentiometer, calomel electrode, and this potential electrode analyze sample. Next, a potentiometer consists of a reference electrode and an indicator electrode sensor and a device to measure the change in potential during the reaction. Calomel electrode is commonly used as reference electrode and platinum electrode as indicator electrode. The indicator electrode responds rapidly to the changes in potential with respect to the concentration of sunlight, which is converted to electrical signal and displayed as numerical value on potentiometer. Application: estimation of FAS using K2Cr2O7 solution. Procedure: pipette out 25 cm cube of FAS solution into a beaker. Add 2 test tube of dilute H2SO4, immerse the reference indicator electrodes assembly in the solution and connect them to the potentiometer. Note down the EMF of the cell before the addition of titrant from the burette. Now add a 0.5 ml of K2Cr2O7 from the semi-micro burette. Allow the solution to mix well and measure the potential. Continue the procedure till a sudden rise in EMF of the cell is observed. Take about 5 to 6 more readings and tabulate the readings as mentioned below. Determine the endpoint of the plotting delta E by delta V versus volume of K2Cr2O7 as shown in the figure. Like this. Then the calculation goes like nominality of FAS is equal to nominality of K2Cr2O7 X into volume of K2Cr2O7 volume of FAS is equal to this. Then we will be getting the weight of FAS per liter. Conductometric sensor. It is used to determine the endpoint of acid-base titration by observing the change in specific conductance of solution. The principle underlying conductometric titration is the replacement of ions of particular conductivity by ions of different conductivity during titration. It is based on Ohm's law. It states that the current I flowing through a conductor is directly proportional to the applied potential and inversely proportional to the resistance. I is equals to E by rho r. E is equals to IR. The reciprocal of resistance is called conductance. C is equal to 1 by R is equals to 1 by rho X A by L per ohm. Siemens. The reciprocal of specific resistance is specific conductance K kappa 1 by R or 1 by A or C 1 by alpha. The specific conductance is defined as the conductance of the solution, which is placed between two electrodes of 1 centimeter apart, having unit area of cross section. The conductance of a solution depends on temperature, number of ions, and their mobility. Instrumentation. Instrumentation consists of two platinum electrode, each of unit area of cross section placed unit distance apart. The electrodes are dipped in the electrolyte solution taken in a beaker and connected to a conductance measuring device. Conductivity metal NaOH, conductivity cell HCl. Applications: conductometric titrations are used to estimate a mixture of weak acid and strong acid, estimate the concentration of colored or turbid solutions, which cannot be titrated using indicators. Estimate weak acids or bases where no suitable indicators are available. Estimate very dilute solutions. Example, estimation of weak acid CH3COOH using strong base, that is NaOH. CH3COOH plus NaOH gives CH3COONaH2O. Initially, conductance is very low because acetic acid is weak electrolyte. When NaOH is added to the acid, the salt formed is highly ionized and hence conductance increases. And complex neutralization of the acid, further addition of base leads to an increase in the number of OH minus ions, hence the conductance increases sharply. A plot of conductance against the volume of base added is shown in the figure. The point of intersection of two curves gives the neutralization point. Procedure: prepare out 50 ml of acetic acid into beaker. Immerse a conductometric sensor in the solution and connect them to the conductor meter. Note down the conductivity of the solution before the addition of NaOH from the burette. Now add 0.5 ml of NaOH from the semi-micro burette. Allow the solution to mix well and measure the conductance. Continue the procedure till the acid is completely neutralized. Take about 5 to 6 more readings after neutralization and tabulate the reading as mentioned below. Determine the neutralization reaction point by plotting conductance versus volume of NaOH as shown in the figure. From endpoint, find the normality of CH3COH and calculate the amount of CH3COH per dm cube as shown in the figure. Normality of CH3COH is equals to N normality of NaOH, volume of NaOH x by volume of CH3COOH. That's it. Thank you for watching. Do like, share and subscribe to my channel.